introducing you about the ecology and environment is basically give an overview of hydrology, hydrological process or the hydrological cycle, with introducing you to integrated water resource management. Okay. So, it is good that most of you have hydrology background. So, it makes life little easier to go through a refresher course on hydrology, but it is also a little tough to keep you engaged, right, since most of the things you might already be knowing, right. Now, most of the problems that we are trying to solve is basically to address the water security and food security, right, and even the eco-hydrology that we are looking, we can look it from different perspectives, and one of the perspectives that we are trying to achieve is to achieve a water resource or so basically to achieve a water and food security, right. So, at the end of this course or sorry at the end of this lecture, what we envisage that you achieve is to acquaint yourselves with the concepts of integrated water resource management and hydrological process and hydrological cycle, know basic methods to estimate water balance components, understand the interactions between the ecosystems and hydrological processes, right. So, when we talk about water security and food security, one thing that comes to our mind, as in the previous lecture what sir was telling, we were started with damming the rivers to increase the water availability. So, we have always considered, or traditionally we have always considered it to be a individual system where we are trying to solve one problem at a time. Similarly, with green revolution, we were only focused on increasing the food productivity, and that is where when we do not consider the interactions between different systems, that is where the challenge comes or the problem starts coming up, right, and that is where the integrated water resource management helps, right. So, your sustainable water resource development consists of exploring the relationship between economic development, environmental quality and social equity. So, your integrated water resource management focuses on meeting the economic and social development while maintaining the sustainability of vital ecosystems. We do not want the resources to get exhausted while meeting the current demand, and that is where your IWRM comes into pictures, integrated water resource management. We want to integrate different systems into our sustainable water resources management plans, right. So, we have most of our rivers are dammed now, or most of the locations where we could construct the dams are constructed already. Now, we are moving into something called as interlinking of rivers. Government of India is focusing on interlinking of rivers. So, we are transferring the water from a water surplus basin to a water scarce basin, right, and in that process obviously the water scarcity or water availability will increase, food productivity will also increase, because on the way much of the area will come under irrigation. But then what are the environmental challenges that it may arise, or what will it have its impact on the hydrological cycle, right. So, nowadays we are focusing more on the IWRM, right. So, IWRM, there are three main concepts. One is the systematic consideration of various dimensions of water. So, it is not only always the water quantity, we also must consider what is the water quality as well, right. And most of the time we are focusing on increasing the water availability, but then water quality takes a back seat, right, and both we have to consider both surface and groundwater system. Although the system concept helps us in understanding the water resources, but we also must be knowing that it is a component that interacts with other systems, right. For example, ecological system, right, ecosystem, other ecosystems, it has an interaction, and we must acknowledge that component, and the interrelationship between the water and social and economic development, right. And so, any development from the environment, from the economic side or the social development involves water as a sector, right. Now, integrated water resource management had 4 principles as defined by the International Conference on Water and Environment organized in Dublin, the Dublin Principles in 1992. They said the 4 principles are water as a finite and vulnerable resource, a participatory approach to solve water resource problems, central role of women and economic value of water. So, coming to each one of them, your fresh water resources that are available comes from your hydrological cycle, right. Although our demands are increasing for development side, but the quantity of water that comes in terms of fresh water from the hydrological cycle is a very finite resource. So, we need to manage that. So, unless we recognize that water as a finite resource, our management plans will be quite chaotic. The second one is a participatory approach. There are multiple stakeholders that are involved in water resource management, and it is always important that all the stakeholders participate in this decision making process, right. It should not be a top-down approach where we say that we implement a policy and then it gets implemented. Okay, so it should always be a participatory approach. For example, watershed development that started in 1970s in India with the focus on soil and water conservation. Okay, now in the 1970s when it started, it was more oriented towards a top-down approach where policies were formed, identified areas, soil conservation structures and water conservation structures were constructed. Now in this process, they did not consider the local stakeholders. What has happened is, though these structures were constructed, there was no one to manage them. So probably after a season or a year, those structures or those whatever techniques we have adopted were not fruitful anymore. Okay, and that's where a participatory approach, so participatory watershed management came into picture, where the local stakeholders come, they decide what kind of structures they require, what are the problems, a discussion, and then it takes into the solutions that gets developed. And it also helps in knowing the local problems. All problems are not same. The problem that is you are facing here may be completely different from there. So one solution will not fit at all locations. So that's where the participatory approach helps. Third one is your women play a central role. Many of your water management, especially in the rural areas, your domestic or even the domestic water requirement, women play a central role. So they should be involved in this entire decision-making process, right? In many locations, women are marginalized; they are not part of the decision-making body. So if we bring them, the water management improves a bit. And fourth one, water as an economic value, right? You might have heard about this virtual water trade, right? Each drop of water has some value. Although water in itself is a free resource. You get from precipitation, you take from the flow, it's a free resource. But the infrastructure that is required to draw some utilization of water has some cost. Your dam costs. Your infrastructure to transport the water has some cost associated to it. So water as an economic value, and this must be considered in your developing plans for maximizing your benefits, right? Water as an economic resource or economic value must be considered, right? So these are the four principles of the integrated water resource management, and it helps us in achieving the sustainable development goals, right? Your integrated water resource management is actually one of the United Nations Sustainable Development Goals, and it has some ways on how it is achieved. It has some metrics to see whether how much it is achieved, right? So it has different components. One is the sustainable development, which has social equity, environmental sustainability, and economic efficiency. At the same time, it has water security dimensions, such as domestic water security, water-related risk resilience, environmental water security, agricultural water security, and economic water security, right? So IWRM is a tool to boost economic growth while ensuring social well-being and environmental health. It's a way to reach the sustainable development goal, right? So if you see United Nations Sustainable Development Goals target 6.5 aims to implement integrated water resource management at all levels, right? Now how do we check it whether it gets implemented or not? There are four key components of IWRM. First is enabling environment, institutions and participation, management instruments, and financing, right? So a successful implementation of IWRM involves choosing and adapting right combination of tools for each unique situation. As I said, each problem is unique, so you need to adopt a unique solution for each particular location. Now let's see these four key pillars, right? First one is enabling environment. So the first part is basically your policy planning, right? Policy level decisions, legislative frameworks that establish certain ground rules for management of water resources. That is what is the first. So do we have certain ground rules? For example, recently we have a ground rule for groundwater extraction. Till few years back, there was no legislation on how much water can be extracted. So if you own the land and if you can dig a bore well, you can extract as much as possible. There was some legislation for the industrial water extraction. For the domestic water extraction, there was no legislation, right? Now what happens? Groundwater is a common resource, right? Even though you may own the land, the groundwater is a common resource. So how much water can be extracted affects your adjoining people, your neighbors, other stakeholders in the system, right? So those kind of legislations are there in place. Then we have institutions and participations. That the political, socio-economic, and administrative institutions are they participating, stakeholder alignment, how do they come up with a common water management solution. Third one is your management instruments, basically the mechanisms that enables decision makers and water users to assess socio-hydrological challenges. Okay? And the fourth one is obviously the financing. Whatever the solutions that you're developing, do we have sufficient funding or sufficient funding support to implement these particular solutions? Okay. So there are some challenges for implementing IWRM. I'm not going in depth into that. Obviously the fragmented governance, because IWRM is applied at different scales. It can be applied at a local scale, regional, national, and at international levels. Then you have limited funding and resources, data limitations and poor information system, stakeholder engagement, climate change impacts, and the conflicting interest from different stakeholders. Okay? But for this to get implemented, IWRM, one thing that we need as engineers or water resources professionals is basically quantification of water resources. Any management, you should be knowing how much water is available. And that is where the hydrological cycle or hydrological process comes into picture. Right? So study of hydrology is essentially we are studying how the water moves from Earth's surface to atmosphere and comes back. It's a cyclic process. Right? Water from the Earth's surface gets evaporated and it comes back in the form of precipitation. Okay? So though we have understood that cycle concept, we are more interested in how do we quantify these resources, or our modeling tools, basically whatever modeling tools that you want to use, want to quantify this resource, right? For example, SCS curve number method. SCS curve number method is a method to quantify how much runoff is generated given a precipitation, right? So for any management, we are interested in to knowing that quantity, the value, right? The previous question, how much runoff gets generated for a 2-inch water, and we had difference on the runoff coefficient method, which is also valid, SCS curve number method. Okay. Now, how do we get that? How do we get that? So this is the hydrological cycle that is released by USGS earlier this year, which is a more comprehensive hydrological cycle, a water cycle which you have been seeing from starting from your high school, but a more comprehensive picture of that. You have evaporation from the oceans, evaporation from the land, and some part of the moisture because of the atmospheric transport comes to the land surface. There will be precipitation, and this precipitation gets divided into runoff and infiltration, which forms into streams. There is snow, melting of glaciers, and from these streams and lakes we extract water for domestic water and industrial usages, and at the same time we release the water back into the water bodies, right? With the waste material comes back to the water bodies, and then there is urban runoff, there are wetlands, and then it finally comes back to ocean, and there is a groundwater and soil moisture that comes into picture, right? So this is the hydrological cycle, and as you see, we are talking only about the water, but the water interacts with various ecosystems as it travels. It's not only we are utilizing, but as it travels on the Earth's surface, it interacts with various ecosystems, and that's where the eco-hydrological modeling comes into picture. So this is a more simplified representation of your hydrological cycle, something that you would have seen before, right? You have a simplified version where water evaporates, forms clouds, comes back in the form of precipitation, and various components. It has surface runoff, infiltration, subsurface flow, groundwater flow. Now in this, the transportation components where the water moves is basically precipitation, evaporation, transpiration, infiltration, and runoff. And in your system, there is a storage components as well, which is depression storage, soil moisture storage, and groundwater storage. Okay. So we are interested in quantifying these components to help us understand how much water is available, so that we can have an idea of how do you manage the water. Demands, we know, right? Different demands are known, but how much is available comes from quantifying these particular resources. So let's see each one of them. So there are different components. One way of quantifying is through measurement. Precipitation, we do measure, right? How do we measure? Rain gauges, right? Now, some time back we had a very sparse rain gauge network, but over a period of time, there are automatic weather stations which are being installed at various locations. Our gauging network has increased, or we have now fine resolution data. Even NITW has an automatic weather station installed here, which measures the data almost every minute, right? So now we have data which is available to us at a time step of every 5 minutes, 15 minutes, every 1 day, right? So precipitation measurement is relatively easy. But what about other components of the hydrological cycle? How do we measure evaporation? How do we measure runoff? Runoff measurement, how do we do that? We have stream gauges located at different locations, right, and we do measure. They are basically point measurements. Precipitation, I think I forgot, there are radar measurements as well, which will give you spatial information, and satellite based estimation of precipitation as well, right. Now, in all that, in the measurement, we use the water balance concept, especially in the watershed scale when you are trying to manage basically a mass balance concept or the watershed water balance or hydrological balance, which is basically you take a watershed. I hope all of you know what's a watershed. It's the area that drains to a common outlet, which is bounded by a ridge line. The ridge line helps us creating a boundary condition that no flow comes across the boundary. So, only inflow to this watershed will be in the form of rainfall and some groundwater flow. Groundwater flow does not really conform to the ridge line boundary, but then in general majority of the input comes from the rainfall. Now, within this watershed you can apply a water balance equation or a mass balance, that is the change in storage within this watershed will be equal to input minus output. Input is your precipitation, output is your runoff, groundwater flow, groundwater contribution, evaporation and transpiration. And this change in storage can be change in storage in any of your reservoirs or soil moisture and soil moisture. Soil moisture is one of the major storage component in your watershed, water storage component, right. So, your delta S corresponds to the change in soil, change in water that is available within your watershed. Now, how do we quantify each of these terms, right. So, when I say that I am trying to refresh your hydrology, I have compressed probably a semester long course into 1.5 hour lecture, right, and that is where I am showing some of the equations just to see, to quantify, basically that is what is used in your models, in modeling tools, right. So, probably you already know it, but then just in case. So, the first process that we are going to see is the infiltration process. The rain that comes hits the ground surface and some part of it goes as runoff, some part of it goes as infiltration. Now, the water that gets infiltrated, right, that starts filling the voids in your soil, the pore spaces in the voids start get filled up. That is what the process of infiltration. Now, as this water moves down, it follows a certain path, or if you see it has certain different zones, right, infiltration process. It will initially saturate the top layer, and as the water moves down, it will start filling up all the pores, and that is what we call as wetting zone or wetting front. Now, when the water enters the soil matrix or soil column, it experiences different forces. One is the gravitational force that is acting on it. In addition to that, it will experience a suction force from the soil particles, and while it moves through the interlinked pores, it also experiences the friction. Now, this suction force binds the water particles along the soil particle. Okay. So, as more and more water starts get binding up, your suction forces reduces and your gravitational force is the predominant force. So, when the water that is held against the gravitational force is what we call as field capacity, right. That is the water that is can be held against the gravity. That does not mean that water is completely full, the pores are completely filled up. When the pores are completely filled up and water moves down, that is when we call it as saturation. Okay. Now, this infiltration process, if you want to model, there are different ways, different researchers have developed. Back in 1930s when this research started on quantifying how much water, how much rainfall becomes runoff, that is when many of the equations have come. One of the equations that we commonly use is Horton's equation. So, Horton conducted different experiments across the catchments in US using double ring infiltrometer, rainfall simulators, and as well as the data that they have collected. Now, based on the data that they have collected, what they observed was any soil, any location where infiltration process is or infiltration rate is a decaying process, right. And they saw that it follows a exponential decay, and that is where the Horton's equation has come. So, over a period of time, when during this infiltration process, it starts with a high infiltration rate, comes down and achieves a constant level. That is what we call as it will be morely close to saturated hydraulic conductivity. Okay. So, that particular point. So, a model for your infiltration rate was given by Horton, where he said that infiltration rate at any point of time will be equal to a constant infiltration rate plus the difference of maximum minus minimum, and which is multiplied by a exponentially decaying constant. Okay, so K is a parameter, T is time, Fc is the constant infiltration rate, and F naught is the initial infiltration rate that is there, right. So based on the different experimental data, they realized that the infiltration rate at any particular soil follows a exponential decay function. Now similar to Horton's equation, many other equations have been developed, Kostyakos equation, right, and there are many equations which are there, but one of the commonly used is Horton, so I just introduced that. Now apart from Horton, another model that we use is Green-Amp model, which is an analytical approach, which has a more analytical approach into solving the Richards equation, right. So what they have done is they have simplified the infiltration process. In the earlier figure, I have shown that infiltration, as the water gets infiltrated, there will be some saturated zone, there will be some transmission zone and wetting zone. That means there is a gradation in the soil moisture that is available. So what Green and Amp done is they have simplified the process. They said as the water moves down, it will saturate the soil. That means water will move down only when it fills up all the pores along the depth. So in this process, what it helps is we can apply conservation of mass equation a little bit more properly, and we say that as the wetting front moves down, the soil moisture will increase from initial soil moisture content to a saturation level. Now using the conservation of mass equation and Darcy's equation, which is basically the equation for fluid movement in the unsaturated zone, they developed a Green-Amp method. They have equations which needs to be solved iteratively to come up with a solution. Based on the time, you can know how much is the cumulative infiltration as well as the infiltration rate. Now if you can identify the infiltration rate, area under the infiltration rate curve is basically your volume of water that gets infiltrated. So if you know the rain, if you know the infiltration rate curve, you can estimate what is the runoff. So you have estimated two things here. Given the rainfall, how much water is going into the soil or gets added into soil moisture or soil storage. At the same time, how much water is going as surface runoff or rainfall excess. Now coming to the next component, which is your evapotranspiration. Okay, evapotranspiration is combination of evaporation from open water bodies, soil surface, vegetated surfaces, as well as sublimation from snow and ice. In addition to that, your plants, canopy, they have a transpiration, right? They extract the water from the soil and then they transpire. So the combination of both of them is what is called as evapotranspiration. Now, what are the factors that influence evapotranspiration? What are the two major factors? Temperature, relative humidity, right? So if we both are correct, if we generalize it, basically temperature is basically the energy supplied, solar radiation. So your evapotranspiration or the evapotranspiration process is controlled by two things. One is the energy that is supplied. Second is ability to transport the water vapor. Now any fluid or anything will go from a higher gradient to a lower grade, right? Water moves from higher energy to lower energy. Similarly, your evaporation process is also same. You have water molecules which are higher at number and they go into a place which are having low number. So from a higher energy to a lower energy. In this process of transformation, you need energy to be supplied, and at the same time, when this transport happens, water molecules happens in the atmosphere, if it starts saturating, this rate will reduce. So your water, there should be ability to transport this water molecules away from the location, so that the gradient maintains. That is what is Dalton's law. Okay. Now based on these two principles of energy balance and mass balance, Penman developed the equation, which is what we call as a combination method for a evaporation from open water bodies. And that equation was modified by Montieth, which we now know as Penman-Montieth method, which integrates the energy balance as well as the aerodynamic method or mass balance, right? And in addition to that, we also recognize that each crop or each plant transpires differently. The amount of water extracted and the amount of water the transpiration takes place depends upon the crop characteristics. So they introduced the crop resistance factors, aerodynamic resistance factor as well as the surface resistance factor. Aerodynamic resistance factor is primarily to the obstruction that is caused to the wind, and surface resistance factor is basically a crop factor that depends from one crop to another. Okay. So, using this Penman-Montieth method, we can estimate the potential evapotranspiration, that is, what is the maximum evapotranspiration that can occur at a particular location. Now, there are ways to measure the evapotranspiration. One of the ways is your lysimeter, which will give you the potential evapotranspiration. It also works on mass balance. It measures all other water balance components, and you can measure the evapotranspiration by using a simple mass balance. And for the evaporation, you have pan evaporimeter, which are placed across most of the reservoirs to estimate how much water is being lost from your reservoirs. Okay. Now, coming to the runoff. Runoff is something that most of us are interested in, right? How much quantity of water is available, right? Most of our research happens on the runoff. So, there are two ways of runoff generation. First one is what we known as Hortonian overland flow. This is when your rainfall rate is higher than the infiltration capacity. That means your input rate is higher than what the infiltration of particular soil. So, if your rainfall intensity is higher, it will start ponding on the surface and it will flow. The water surface runoff will flow. So, though there will be infiltration happening, since the rainfall intensity is higher, it will be much lower. The second type of runoff generation is saturation excess overland flow, right? Where your soil is saturated, probably because of the previous rainfall or probably because of the subsurface processes, subsurface transport of water. Now, as more rainfall comes, it starts ponding on the water and it becomes runoff excess or surface runoff. Now, both these processes may be happening in the same watershed, same location, and they are interchangeable. It is not necessary that at a particular location only Hortonian overland flow will be there. It is entirely possible it starts with Hortonian overland flow and gradually becomes a saturation excess overland flow. Okay. Now, as more and more water starts building up in the watershed, it starts flowing. As I said, water flows from higher energy to lower energy. Now, in that process, at the watershed outlet, at the outlet point where we start measuring, you see something called as a hydrograph. That is the time distribution of discharge, usually we measure it in cubic meters per second with respect to time. Okay. So, this is your hydrograph that we are interested in. Area under this curve is the volume of runoff or volume of water that is coming at this particular point. Now, in this hydrograph, we are interested in two components. One is the volume. How much is the excess runoff that we are getting? And second thing is, what is the peak? Many of our flood, or not only flood, many of our designs or even for water quality measurements, we are interested in what is the peak flow and what is the minimum flow that is coming. So, to estimate the volume, one of the method is what we call as SCS curve number method or NRCS curve number method, right? It was initially SCS, Soil Conservation Service, now it is Natural Resources Conservation Commission. Okay. So, you have different equations, right? You have Q is equal to pi P minus IA whole square by P minus IA plus S, where IA is initial abstraction. So, all this is resultant of various experiments that were carried out in US by United States of Department of Agriculture. And in that process, when they conducted different experiments, they realized that when a rainfall is received, when rainfall comes, some part of it takes some time for the runoff to start. That means some amount of water is gets either infiltrated or gets stored in your system. So, before the runoff to start, some storage has to be filled up. Now, once the storage gets filled up, runoff increases and it will start to follow more linearly with the rainfall amount, right? And that is what is your initial abstraction. Some amount of rainfall corresponds to the canopy storage, depression storage, and some soil moisture, right? So, once that gets satisfied, the remaining precipitation is some part of it will be infiltrated and some part of it will be going into runoff. So, based on that principle, they have developed a equation Q is equal to P minus IA, and they have introduced a parameter of maximum retention, where S is equal to 25400 by curve number minus 254. This is in millimeters. They introduced something called as curve number. So, during their experiments, they realized that your runoff, amount of runoff or the hydrograph depends upon various factors. What are the land use? What is the soil? What was the condition of the watershed when the rain started, as well as what was its rainfall characteristics. Now, based on the soil and the land use, curve numbers were defined. They were the major factors, right. So, in the previous lecture we talked about runoff from a pavemented catchment as compared to a vegetated area. So, vegetated area you will have less runoff as compared to a pavemented catchment, right. So, based on these factors we were able to develop a relationship between runoff and precipitation. Now, S is a fact, S or the maximum possible retention depends upon the watershed characteristics, which usually does not change with time, or even if it changes we can update them, but precipitation which changes with time you can get what is the runoff. So, this will give you what is the volume or depth of runoff for a particular rainfall event at a particular location. Now, the second component is the peak. So, to estimate the peak we use the rational method, which is gives you the peak of your hydrograph. Given the rainfall intensity, it gives you peak of the hydrograph. Now, how does it do that? Now, if you take a particular catchment, let us say NIT Warangal, and you have received or you are receiving a rainfall for a infinite duration of time, what will happen? Your hydrograph will start increasing, it will attain a peak value when your entire catchment starts contributing, and it will continue to be there till the rainfall ends. Now, at this point where the peak flow is occurring, that is when what is your inflow? That is rainfall intensity I multiplied by catchment area. That is volume of rainfall that is you are receiving, or the discharge that is receiving in the entire catchment. Now, we also know that not all rainfall becomes runoff. So, there is a rainfall coefficient, and that is what runoff coefficient, sorry. You have a equation Q is equal to CIA, 3.6 is basically a unit conversion factor, but rational formula is Q is equal to C into I into A, where A is the area of the watershed, I is the rainfall intensity, and C is runoff coefficients, and discharge Q is the discharge. Okay. Now, your I, we use this rational formula for design of various hydraulic structures, where you use I corresponding to the time of concentration of your watershed. Okay. And area A is area of catchment, and you can have different empirical formulas to estimate the I from the given data set. Okay. Now, for a larger catchments, though these are all models which will give you individual components of your hydrological cycle, we have simulation models such as HMS and SWAT which integrate all these processes, right. Either all of these processes or at least some of these processes, right. SWAT does integrate all these processes, where the runoff estimation is done by SCS curve number method and Greenamp method, you can choose. Evapotranspiration estimation is done using Penman-Montieth method, Hargreaves method, right, and the routing happens using Muskingum method or variable storage method, right. So, different models assimilate these processes to form a simulation model at a watershed scale, right. Whatever we have seen in the previous few slides are basically individual processes. Now, you integrate them in your mass balance equation to have a more comprehensive understanding of your system at the watershed level. Okay. Now, that is the basics of the hydrological refresher. Now, if we move forward, what does the anthropogenic activities, how does it affect the hydrological cycle, right? Can anyone tell how our activities affect hydrological cycle? Urbanization, deforestation. So, how does urbanization affect? It decreases the infiltration. We consume more water. Yes. What else? Quality of water. Yes. What else? More rainfall may come because of the microclimate changes. Reflectance on the surface changes, increasing global climate change. It increases the runoff because of the paved area, and it also reduces the evaporation, evapotranspiration, right? Now, your feedback system is disrupted because of the urbanization. Whatever the feedback system was there, it has disrupted. Okay, so that causes urbanization. Any other human activity that affects hydrological cycle? Dams and reservoirs, yes. You have large water bodies stored, which was not there earlier, so you will have higher evaporation, which will lead to changes in hydrological cycle. Anything else? Irrigation, yes. Agriculture, right? Agriculture in general has an effect on hydrological cycle. You are growing certain crops. Now, each crop will have a different amount of water that it transpires, right? So, few years back you would have had a rainfed agriculture, where you would have depended entirely on rainfall, and you were growing certain crops which were not water intensive. Now, with irrigation available to you, you start growing more water intensive crops like paddy, sugarcane, right? And they also transpire lot of water. So, in this process you will have some changes to the feedback to the atmosphere, right? Telangana, few years back it was mostly dry land agriculture, but now if you see, much of the landscape has changed to more of a paddy growing or rice growing, right, where you need the soil to be saturated. If soil is saturated, what does it mean? Whatever is the atmospheric demand in terms of potential evapotranspiration is being met, which earlier it was not being. That means the evaporation from the surface is increasing. So, there is a change in the system. Obviously, irrigation, when you are irrigating, again the evaporation is changing. And in addition to other factors, we do lot of afforestation, right? Yes, which we see it as a way of bringing back to original, but that also changes the hydrological cycle, right? So, all and every anthropogenic activities have a certain effect on the hydrological cycle, right? Change is inevitable, but the rate of change gets affected by our activities, right? So, urbanization, as I said, it affects farming, and cities use irrigation, and application of fertilizers and pesticides lead to environmental problems. Pollutants cause algal blooms, spread diseases, harm wildlife and habitats. Your damming of the rivers cause the change in your aquatic ecosystem. Interlinking of the river causes changes in the aquatic ecosystem, right, because water quality will be different from one river to another river. The sediment will be different, causing a change in your habitat itself. So, urbanization, industrialization, population growth impact the landscapes and watershed hydrology, right. It alters the hydrological cycle, requiring water surfaces like supply, drainage and wastewater management. We need lot of management to address this. Okay. So, this is a flow chart where you have different things for a urban area. Urban areas, now we are seeing that they are more prone to flooding because of high intensity rainfalls, right, caused due to various reasons. Now, your drainage systems can increase runoff velocity and volume, right, to most of your drainage systems, and we feel that our drainage systems are not sufficient enough to meet different demands, right. So, and then you have impacts on evapotranspiration by reducing vegetative covers, and then growing system, and we do require this infrastructure, right. If you don't have urban areas, you will not be, all of us require this urban infrastructure, right, and other, but then there should always be a trade off between how much to make and what is its effect on the hydrological cycle. Another component on the effect of water cycle is climate change, something that we have been hearing, right, or something that has been almost ingrained into us. Everyone knows, even the school kids know what is climate change, right, warming of the environment. So, what happens in warming of environment? Why is climate change so important, especially in terms of water cycle or hydrological cycle? Rainfall pattern changes. Why does it change? Increasing level of carbon dioxide, yes. Elevated temperatures will create a difference in cycle, yes. It disturbs the energy balance, okay. Anything else? Aerosol concentration changes, yes. Anything else? So climate change, when you basically all of you are correct, you have a temperature is increasing, right? When the temperature is increasing, your atmosphere has a certain ability to hold the water vapor, and that is dependent on temperature. As the temperature increases, it has more ability to hold the water vapor, right? Ability to hold the water vapor increases with increasing temperature. Now that is what, when you have more ability to hold the water vapor, it leads to more intensified extreme events. Your extreme precipitations or lack of precipitations is because of this enhanced holding of water vapor in your atmosphere. That is what is your climate change, right? Now, it's not only extremes. Now, because of changing precipitation patterns, our utilization patterns change. Earlier, probably if you are dependent only on rainfall, you are dependent only on surface water resources. Now, because of these changing precipitation patterns, you are now drawing more water from groundwater, right? So your lakes are getting dried up. Okay. So our utilization patterns are also changing. So climate change. In addition to that, your biodiversity get affected because of changing precipitation patterns. Some of the areas are getting dried up. Forest fires. They are all leading to different changes in ecosystems, right? So your impact of climate change is not only on hydrological cycle, but also in the entire ecosystem that is driven through changes in water cycle as such, right? And that is where it is important for us to understand how these changes are taking place and what impacts it has on the hydrological cycle. Now coming to the hydrological process in ecosystems, linking it to the ecosystem part, we have both surface and subsurface processes, right? We have surface processes such as runoff, precipitation and evapotranspiration, and subsurface processes such as infiltration and groundwater flow. And both of them are important to maintain the ecosystem balance, right? It's not only the surface water resources, we are also interested in subsurface water resources, and the balance must be maintained between them, right? So your hydrological process, flow of water, controls nutrient flow in addition to the water flow, how much nutrient is getting transported, habitat, aquatic ecosystem, and water availability, which directly or indirectly influences the biodiversity and ecosystem, right? For example, there were some examples of water availability of African elephants. They are more prone to less water available, right? They are adapted to less water availability. Similarly, this hydrological process contribute to know water availability at spatial locations, not at one particular point, but spatially how does the water availability is changing. Now this changing water availability in space affects the ecosystem and biodiversity as such, okay. Now in addition to that, your surface runoff or precipitation patterns affect soil erosion, which also increase the nutrient transport. The fertilizers or pesticides that we apply, much of it is in your soil. Now in this erosion process, as the soil gets transported, soil particles get transported, the nutrients also gets transported. It's where your aquatic system gets affected, right? Then subsurface flow promotes water recharge and supports plant growth. Many of your forested areas have deep roots. So even if it doesn't rain for quite some time, they can extract water from the subsurface layers, okay? So the interaction between surface and subsurface processes regulates water availability for your ecosystems, okay? Another part is impact of land use changes on hydrological processes and ecosystem services, right? Your land use changes, as we said, urbanization, changes in your cropping pattern, changes in land use from forested area to agriculture, all of them affect the hydrological cycle, right? So for example, as I said, the Telangana case study, where we used to have a dryland agriculture mostly, it was predominantly a dryland area. Now because of this lift irrigation schemes, at least the Karimnagar district is called as the rice bowl of Telangana, right? It has completely into a paddy cultivated zone, okay? So what happens when we move from a dryland agriculture to a paddy dominated this thing. One is your water requirement increases, right? Second thing, your evaporation is going to increase. Now, with more and more area that comes under rice and more water availability, farmers may go for 2 crops of rice or 3 crops of rice, which affects the soil nutrients, where each plant will be extracting nutrients from the soil. Now, if you keep growing only one kind of crop, your nutrients start getting depleted. Now, to replenish those nutrients, we start applying fertilizers, and only some part of that fertilizer is being assimilated by the plant. Remaining goes as runoff, right? Some of it goes leached out to groundwater, so groundwater contamination. Punjab is a classic case, right? Groundwater got contaminated because of excess use of fertilizers, right? So similarly, same issues might happen. So when we have these kind of systems, we also must be considering what are its effects on the hydrological cycle. That's where it's important. So the impact of hydrological processes on the ecosystem services. So basically, your hydrological processes are fundamentals to ecosystem services like water availability, flood regulation, and habitat provision. And then you have human interventions in hydrological cycle impact assessments, ability to provide these services, and a functioning hydrological cycle is essential to meet these particular services, right? We will talk about ecosystem services later in this course, right? But then all these components are important in managing our water resources, right? So with that, I'll stop here. So if you have any questions, we can take up. No questions? Yes, yes.
Whatever that they are doing. If it is the installation of hydraulic structure or whatever policy that they are proposing, the stakeholders are mostly concentrating on the side of the people who are benefiting. So, how does the